At Apex Services, the production line is failing. Machines seize violently, bottlenecks compound by the hour, and unfinished products stack up across the factory floor. When a manufacturing system collapses, the instinct is to push operators to simply work harder. But improving efficiency is a precise science, not a matter of effort. It requires engineering the complete elimination of all operational losses, specifically waste or Muda, unevenness or mura, and strain, known as muri. To transform this failing assembly line into a hyper-efficient system, industrial engineers do not rely on intuition. They deploy a highly specific stack of analytical tools to dissect the production process and armor it against failure. This transformation begins by stripping away ad hoc troubleshooting entirely. In its place, engineers enforce a rigid epistemological framework known as the QC story. Without this strict diagnostic structure, any attempt to fix a manufacturing line is just guessing at the symptoms. The QC story ensures that engineers are actually curing the underlying disease. The QC story is a standardized sequence of problem-solving steps. It forces teams to move logically from the initial selection of a theme all the way through to final standardization, ensuring no critical data is skipped. This table maps specific analytical methods for each phase of the QC story, aligning tools like Pareto diagrams to their exact stage. The crucial juncture is step 2, capturing the status quo. Before a hypothesis is formed, the exact current state must be quantified. To capture this reality, teams utilize structured brainstorming. This is strictly governed by 4 rules: absolute zero criticism of ideas, encouraging freewheeling thought, prioritizing the sheer quantity of observations, and associating distinct concepts together. Those raw observations are then organized using the KJ method. The KJ method is a structural tool that categorizes massive amounts of qualitative data by their underlying similarities, extracting objective patterns from the noise of the factory floor. By enforcing the QC story framework from day one, engineers lock out premature assumptions. Every subsequent countermeasure they design will be rooted entirely in verified structural data. With the baseline established, the active problem-solving phase at Apex Services begins. The objective now is to isolate the exact mechanisms causing the line to fail. For acute logical anomalies, like a sudden machine stoppage or an obvious product defect, engineers apply YY analysis. This diagram illustrates the branching logical structure of a YY tree. By taking a specific phenomenon, such as small bugs entering a workspace, investigators can trace the exact chain of events backward to find the true source. Methodologically, the team must drill down repeatedly, asking why up to 5 levels deep. They cannot stop at broad environmental factors. They must reach the foundational mechanical or procedural cause. This requires a strict rule of backtracking. Once a causal chain is constructed downwards, the logic must be entirely readable in reverse. If cause E triggers D, then D must perfectly explain C, back to the initial phenomenon. If a single branch fails this reverse logic test, the entire analysis is deemed invalid. The team must restart to ensure they haven't omitted a critical variable. Why-what analysis takes a chaotic, multivariable anomaly and forces it into a linear, solvable equation. It guarantees that the resulting countermeasures permanently neutralize the root, rather than temporarily patching the symptom. Acute anomalies are linear, but chronic losses, the subtle, persistent defects that drain efficiency over time, often defy conventional logic trees. In these cases, the critical factors are hidden or deeply intertwined. To solve these, engineers rely on PM analysis. PM analysis is a diagnostic approach that abandons operator assumptions entirely, forcing the team to analyze the failure strictly through its physical mechanisms. We can observe this physical deconstruction using the mechanics of a simple flashlight. When it fails to turn on, PM analysis doesn't guess the cause. It lists the absolute physical conditions required for the phenomenon of light to occur. First, the mechanism requires a power source. The battery must possess enough internal energy to generate heat through an electric current. Next, PM analysis maps the remaining rules. The path of electron flow must be completely free of rust or disconnection, and the incandescent bulb itself must meet exact designated specifications to withstand the current. By isolating every required condition, PM analysis proves that chronic failures are not mysterious occurrences. They are strictly the result of measurable physical principles being violated within the equipment's architecture. Once the mechanical defects are mapped, the focus shifts to the human baseline operation. This is optimized using the IE, or Industrial Engineering Method. This pie chart breaks down an operator's total functional time, forcing management to categorize every single physical motion into one of 3 strict classifications. The central slice represents core tasks, the precise motions that actually manufacture value. Everything else is categorized against it, starting with direct wastes, such as producing defective products or holding excess stock, which must be eliminated immediately. The remaining slice represents associated tasks. These are actions like reaching for tools or unwrapping materials. They produce zero value for the customer, but cannot be eliminated under the current layout. To strip down these non-value tasks, engineers apply the ECRS principles. They interrogate the process to see if tasks can be eliminated completely, combined together, rearranged for better flow, or simplified to save time. This drives the overarching goal of motion study. The objective is to design human motion that maximizes energy efficiency and completely eliminates operator fatigue. Operators are trained in the principles of motion economy. Workstations are redesigned to utilize simultaneous hand movements and gravity feeds while aggressively cutting out needless walking, bending, or searching. The IE method views human physical motion as a finite, highly valuable resource. It must be ruthlessly conserved to achieve maximum operational output. However, perfecting the mechanics of a single operator provides zero economic benefit if the overall production line remains bottlenecked at the very next station. To synchronize the entire floor, engineers measure cycle time. Cycle time is the actual timed duration a single operator requires to complete their specific assigned sequence of steps. They contrast this internal speed limit against talk time. Talk time is the absolute rhythm of customer demand, calculated strictly by dividing the regular operating hours by the total quantity of units required by the market. This pitch diagram visualizes the critical discrepancy between different operator workloads. By plotting the individual cycle times of processes A through E, systemic bottlenecks become immediately visible. The shaded region at the top represents the organization loss. This is the exact volume of wasted capacity and idle labor occurring below the required talk time ceiling. To flatten this chart, engineers rely on the organization efficiency formula. This mathematical tool measures the total net operation loads against the talk time, allowing managers to perfectly redistribute the physical workload across all personnel. Through strict line balance analysis, every node in the production matrix is tuned to beat at the exact same metabolic rate. It prevents both inventory buildup and idle time simultaneously. The final phase moves the factory from reacting to current failures to predicting and neutralizing future defects before they even occur. This predictive risk modeling relies on 2 distinct methodologies: FMEA, which stands for Failure Mode Effects Analysis, and FTA, or Fault Tree Analysis. This schematic maps the directional logic of both predictive systems side by side. FMEA operates bottom-up. It analyzes the failure modes of individual component parts to forecast their potential impact on the wider system, ranking every possible accident by probability and influence. FTA takes the exact inverse approach. Operating top-down, it starts with an undesirable catastrophic event, like a total conveyor shutdown, and deduces the compound electrical or mechanical faults that could logically trigger it. At Apex Services, the production line now moves with absolute synchronized precision. Because the line is physically stabilized and risk-proofed, value analysis can finally be applied. Value analysis evaluates the functions of the product itself, sourcing minimum cost material alternatives without degrading the necessary performance. This state of operation is the result of a complete engineering stack, enforcing the rigid QC Story framework, executing physical PM deconstruction, balancing the line mathematics, and deploying FMEA predictive models. Operational perfection at an industrial scale is never an accident. It is the deliberate mathematical eradication of the unknown from the manufacturing environment.